Hello and welcome to Anthony Trans and Cameron Angle's Calculus project. And today we're going to be talking about how calculus relates to probability. But before we do that, we need to quickly cover some basic concepts that will be important as we learn the calculus aspect. And you will see a couple examples later on. The first concept we're going to talk about is a random variable. A basic random variable is an uppercase letter that can take on any random value or any property. For example, I would always have to write down capital P, open parentheses, heads on a coin flip, close parentheses, equaling 0.5 or 50%. Now I can substitute in an uppercase letter for what I would need to usually write down with that letter. So now I can write down capital P or capital G equaling 0.5 or 50%, and capital G will replace heads on a coin flip. Now, any value would mean that if I land on heads, capital G would equal any value I assign to heads. So capital G would have to equal the number that I assign to. So I would assign, 45 to be heads, and vice versa for tails. So I would assign 26 for tails. Now, these variables can be categorized into two categories: discrete and continuous. A discrete random variable are finite numbers. There is no other value that the random variable can take except for the numbers that you pick. For example, if capital X is noted as 1 for a person born in a classroom on 1994, 2 for another person born on 1995, and 3 for the same person in a classroom born on 1996. These would be discrete random variables because it can only take on those values. Also, because it's easily listable, it is discrete as well. Note, regardless of how big the number is, it's still write downable by solid numbers with no decimals at all. It's discrete. For example, no one can really take the time to count how many ants are born tomorrow in the entire world at once. It cannot take on an infinite number though, so it is still a discrete random variable. However, a continuous random variable can take on any number between two extrema. For example, if capital U is noted as the exact mass of any animal at our local zoo, if I would measure it and it would read 123.54 pounds. But since I'm looking for exact values, I need to go even further, like 123.543323246345 pounds. Even then, it's not that accurate because I need to keep going to the infinite decimal place. And the two extrema I'm measuring it from is 0 pounds to the biggest weighing animal to date, also to the infinite decimal place. So this is continuous because it can take on any value within these two extrema. In short, it's impossible to list. For example, the exact time on a runner finishing a 400-meter dash from 0, which is not participating at all, to the speed of light and beyond, then it is a continuous function because you have to account for the many decimal places that are between two decimals. But thanks to tolerance, we can cut things close. So going back to the earlier example of the exact mass weighing in a zoo, I would need to write down to 2 decimal places because I do not want to sit there and count how many decimal places this animal exactly weighs. On a graph, the discrete random variables can take on a bar graph, while a continuous random variable will take on some curve function that involves taking the area under.
And that's where I come in. Technically, you can find the area under a discrete probability function, and it's actually pretty easy. Like here. You want to find the probability of either option 1 or option 2? Base times height, add them together, and you're done. It is a bit trickier with continuous probability, so first I'd like to talk a little bit about how these functions get made. Say you're at some weather station that actually gets their stuff right somehow, and you're measuring the probability of rainfall in an area. When we hear chances of 2 inches of rain, they're not talking exactly 2 inches. It's physically impossible to measure. There's usually some kind of leeway based off the measurements at hand. So if we're going by a probability of single inches, odds are we'll be fuzzing the lines every half inch. So this is measured by this. That way we'll get the general idea, and the weathermen can be as right as the horoscopes. However, if we could make this more exact, why don't we? So this becomes this, becomes this, and so on. It gets to a point where we're measuring by increments infinitely small. Ignoring all the vertical lines, our graph would end up looking like this. 2 inches of rain is still our peak. The proportions are all the same. We're just being really, really exact. And just like with the discrete function, all we have to do to measure the probability in a range is to find the area under the curve. This, essentially. So, random question. What's the probability of it raining 2 inches according to our new function? When we checked the discrete function, it was a half chance at 0.5 probability. So, obviously, the probability of it raining 2 inches is 0. What, don't believe me? You're measuring the area of a line. A single line. A single line exactly at the x-coordinate for 2 inches. So there's no area. No chance of it raining 2 inches. Between 1.99 and 2.01 we can do. Between 1.99999 and 2.00001 we can do. But exactly 2? Nada. And this brings me to my final point. These are probability curves, right? Functions of the odds that something will happen at random. So if we were to take the area under the entire function, what would we get? Anybody? Oh, yes, Cameron. Exactly. Because the total probability of all possible outcomes added together is, say it with me now, 1. And so I'll leave you with this final problem, straight out of the book. Is this thing on the board a probability function? And if it is, what are the odds of x being between 4 and 8?